Okay, few announcements. One is Nicholas, are you still on the call? Um, if not, Nicholas has done a great job of this. I put in the chat a link to a tutorial site for the Fab Academy, and it had recently not been updated. And so he's driving a refresh of it. So in addition to the weekly material, these are supporting tutorials for each week. And through the cycle, we'll be filling this in. So a really nice job from Nicholas working with Julian to wake that up. A second note is, excuse me, March 8, the US switches daylight savings time. Oh, I'm going to interrupt myself. Blair, I see you're on the call. Were you here when there was a woman from Charlotte who mentioned you as an inspiration?
Yeah, we did a podcast with Cooperation Jackson. Good to know. You never know who you're speaking to and who will pick up on things. I
Okay, so
really appreciate the direction he's going with the social impact work also. Thanks.
great. So Charlotte meet Blair, Blair meet Charlotte. Nice. Um, so speaking of confusing, daylight savings time in the US is March 8, and multiple parts of the world change at different times and don't change. We keep it locked to 9 a.m. in Boston to control the limits from the Pacific, one side to the other side of the Pacific Ocean. So next week is normal, but the week after will be confusing for some places. Nicholas has done another nice thing of put together a calendar invite to automatically adjust it. So at next week's class, I'll go over the time zone tracking. This is just a 1 week in advance alert to be ready for that. So with that, you 3D printed the week before you programmed. We're back to electronics this week. And so today you're going to design electronics. Next week we go back in the lab and you're going to do large format machining, make something big. Week after that, you then get to produce your electronics. So this week's assignment is you're going to design and simulate a circuit board. And I have three featured examples. Adrian, who you've gotten to know well, I assume, did a great job on this assignment. He designed a general purpose programmable module and then interfaced it to all of the kinds of inputs and output devices I'll be coming. Pablo, I'll ignore that question. Then Annie, okay, Nicholas is back on. Just Nicholas, I mentioned, yeah, just I mentioned you're doing a nice job waking up the tutorials and also made a convenient invite for the time zones. Yep. So Annie, the reason I'm showing this is most circuit boards are boring rectangles, but you don't have to do that. So like when she did this assignment, she decided to make me for a circuit board. Circuit boards don't need to simply be straight lines in rectangles. And then the electronics design tools are powerful, but can be frustrating. Kai got annoyed with them. So he said, I don't need them. I'm going to make my own tool. And one of the non-trivial things about electronics design is arranging and packing and laying out, which we'll talk about. So he wrote this script to do this gorgeous job of you give it your input design and it smushes it all together. And he just wrote the script to do that, bypassing the tools I'm going to teach you. So that's another inspiration. So to do the assignment, we need to cover two big topics today. One is what are the components?
Neil, you muted.
Sorry, I just cleared my throat. You won't master this today. View this as you're on a promontory looking out over a fertile valley. And today you'll see the valley. And in the coming weeks, you'll be hiking through the valley. As a reminder, at the top of each page is a link to the inventory. This is the electronics inventory in the labs. It looks like a long list, but by the end, you'll understand everything in there. This next link is to, this is a class I teach on the physics of information technology. That explains how the devices work. I'll just assume that, but if you want to go deeper, that's a resource. This link is to a beloved book, Art of Electronics. You should all have this handy in your lab. It's not an electrical engineering book. It's a book full of tips and tricks, what works and what doesn't. Strongly recommended. So first thing we need to cover is what are the parts you can use? And then the second thing we'll cover is how do you place the parts to design a PCB? This week is all design, and then in 2 weeks, you'll make the circuit board you design. So wire, we use ribbon cable. A lot of these links are DigiKey, the vendor. They cover global. In the US, this is the one I use most. This is ribbon cable. We generally don't put in rolls of separate wire because one of the handy things you can do with ribbon cable is peel it apart, and you can pick out how many traces you want. It's specified by the pitch of the wire, and that's important for the connectors I'll talk about. And then a key parameter is AWG. AWG is the wire gauge, and you can find easily tables of AWG versus current. And so fatter wire is less resistive, which means it can handle more current. And so you size the wire to the load going through it. So we use rolls of the ribbon cable. Then, I'll have to fix that link. These links appear in class because parts are always coming and going, becoming obsolete. So I'll figure out what's wrong with that link. But what the link was for is an IDC connector like this does something somewhat magical. When you have the wire and you want to put a connector to plug it into a circuit, the straightforward thing is you have to put a connector on each wire. But what these IDC, which means insulation displacement connector, does is they have fingers, and the fingers have a little sharp gap. And so you bring the ribbon cable in and you push it down into the fingers. The fingers are just the right size to cut through the insulation and contact the wire inside. And then you put on a clip that strain relieves it so you don't pull on that. And so in one operation, it lets you terminate the ribbon cable in a connector you can plug into your circuit board. And about a third of the inventory in the lab all of this is just connectors for all kinds of different connector purposes. Kieran is asking about RJ45. Those are different. It's similar but different. Yeah. So that's a connector. We use buttons. Here's this classic button, and I'll be going back and forth. The button, you can draw it. That's a switch. A button, typically, you draw like that. It's normally open. You push to close it. And they come in a wide variety of sizes and shapes. So this is a surface mount one. For something like this one, these two pads are connected, these two pads are connected, and then the button connects between them. So push button. Then this is a switch. Again, surface mount. And so that one, you draw like that. And so in one position, it's like that. And then in the other position, it's down there. And so unlike the button, that one stays where you leave it. So it can be for configuration or, for example, turning power on and off. This is a resistor. Um, Resistors you draw like that. And the current through the resistor is the ratio of the voltage across it divided by the resistance. So in a plumbing analogy, if you think about water flowing in a pipe, the voltage is the height above ground, and the current is how much is flowing. And a resistor is like a constriction that slows it down. And so as we go in today's class, I'll show you a number of places we use resistances. So they're specified by the package size. This one is a 1206 package, which is fairly tiny when you first see it, but large compared to the smallest ones. We use that size package widely in Fab Academy because if you make the pads for it, and you're using a 1/64 inch end mill, there's enough room to put a trace between the pads. So when you route, which I'll talk about today, you can route underneath it. It's specified by the tolerance. This one is 1%. It's specified by the resistance. Remember the ratio of voltage and current. And then an important parameter is how much power it can dissipate. And when we get to power electronics, that'll matter more. Kieran has a nice image of what I said in words in the chat. So lots of use of resistors. When we get to diodes, light emitting diodes, we'll use them to control how bright the diode is. Then capacitors, there's two kinds. Ones we draw like that, and ones we draw asymmetrically. I did that sloppily. Ones we draw asymmetrically. So a capacitor stores charge. The ratio of the charge on the capacitor to the voltage is the value of what's called capacitance. So in a resistor, voltage and current move in the same way. In a capacitor, the current through the capacitor is the capacitance times the rate of change of what's going through it. So capacitors block DC currents, but they let AC currents through. So that's one use of them. And they store charge. And so one use we use is a filter to get rid of, for example, noise. And a common use is we use them to store power. So the polarized capacitors can store much more charge than the unpolarized capacitors, but they're limited in their voltage. So this is a classic 1206 capacitor, and typical values for these are microfarads. And again, it's specified by the capacitance and the voltage that it can handle. Then this is crazy. Not that long ago, these didn't exist. This is what's called a supercapacitor. The last one was a microfarad, 10 to the minus 6 zeros. This is 10 farads. This is 10 million times bigger. It's limited. The last one was 50 volts. This one is limited to 3.8 volts, but it stores a huge amount of charge. And so you can use these as they're kind of halfway to batteries, but they're very easy to charge. And whenever we do things like control motors or powerful speakers, we put big capacitors next to them to store charge. And that's in part for inductance. So an inductor looks like this. And so if we zoom in, the capacitor has charge on the plates and there's an electric field. The inductor is storing a magnetic field. And so in the inductor, it's the opposite of the capacitor. The capacitor current is the rate of change of voltage. The inductor voltage is the rate of change of current. So capacitors block DC and let AC through. Inductors are the opposite. They let DC through and they block AC. So one of their uses is for filters to prevent transients getting into electronics. Now, one reason why capacitors are so important is if you have a power supply over here, and then over here you have, you're driving a motor in your machine. This wire, in effect, has a lot of inductance because there's a magnetic field around it. So if the motor needs more current to handle a load, it's going to take a long time for the current to rise through the inductance. And so we put a capacitor next to the motor that gives it extra charge. These are called bypass capacitors. We put them next to computer chips. When your processor switches, there can be an inrush of current. And so you put a capacitor next to it to help it run. When you don't have these capacitors, it can be really tricky to debug. Like at the Fab Academy instructor boot camp, I had a circuit that used a chip to drive what's called a BLDC motor. And it worked fine for me, and it worked erratically for Quentin. And I hadn't put on a big enough local storage capacitor. When he just added that capacitor, then the motor started working perfectly. So you can get very glitchy behavior when you leave out these sort of components. Crystals tell time. So that's a crystal. They're drawn like this. And that's literally what they are. It's sort of, to explain that, it's a capacitor, but it's made out of what's called a piezoelectric material that when you put a voltage on it, it flexes. And when it flexes, it produces a voltage. And it's like pushing a swing. You drive it resonantly, and you use that to tell time. When you make circuit boards with fast processors from scratch, you need these crystals. For slower processors, they have an okay timekeeper on board, or in the shell, it's built into it. Okay, these are all what are called passive components. Now we get to semiconductors. So diodes we'll use all over the place. A diode, you draw it like that. It looks like an arrow. It has two sides, an anode and a cathode. And the way you remember it is current goes in the direction of the arrow, and it goes in alphabetical order. So if you look at the voltage across the diode versus the current through it, an ideal diode looks like this. In one direction, no current flows. In the other direction, it's a perfect conductor. In actual fact, a diode, it looks more like this. Let's see, Karen is asking, is this classical current or flow of electrons? Current is flow of electrons. Karen, there's no difference. So this is what an actual diode looks like. This is what's called the diode drop. There's a drop, and 0.6 volts is typical. In this reverse direction, it conducts a little bit, and this actually is a sensor. You can detect light or temperature with that. And this quadrant is actually where you make power. That's where solar cells work. They make energy. So we use diodes. One of the ways we use them is to make sure current only goes in, not out. So many of our circuits, if you power them backwards, you'll kill the components. So we use a diode so that if you connect the battery backwards, it doesn't hurt anything. Sam is just noting, I see. Yeah, Sam and now I understand Karen's question. This is a very, very confusing thing. Sorry, Karen, I misunderstood your question. The current flow going from high to low voltage goes in this direction, but because of a mistake in history, the electrons are actually traveling in the opposite direction. So electrons travel backwards to what we call current flow. So Karen, I misunderstood your question. I'm referring to what we call the current flow that goes from high to low voltage. So we use diodes to make current only go in one direction. What are called Schottky diodes have a very low threshold, and all of what we're talking about now is in the notes for the physics book I mentioned. Zener diodes are interesting diodes. You draw them like this with a little step. And what those do is, if we look at current versus voltage, there's a very sharp drop. And at an exact voltage, they suddenly start conducting. So you can use a Zener diode to clip a voltage so it doesn't go beyond a current value. Kieran, that's correct. Electrons are going from ground up to the supply. What we call current goes from the supply down to ground. Now we get to LEDs. So you're likely to use lots of LEDs to make blinky lights. We draw them like a diode with a wiggly line coming out. The LED is specified by the package. It's specified by the brightness that goes from a dim light to it would hurt your eyes. It's specified by the current that it can handle and the divergence angle. And then a key parameter is the wavelength. And these go from infrared all the way up to ultraviolet. There's a really interesting story noting in the chat about the invention of blue LEDs. Now, a LED has a current voltage curve that looks just like this one. And so there's a problem in using them, which is if you have a processor, you take a pin and you connect an LED to it, and then you connect that to ground. When the pin turns on, once you pass the threshold, the current it's going to ask for is essentially infinite. So you're going to saturate the pin of the processor, pulling as much current as it can generate. And it could be too much for the LED, and you could literally blow up the LED, or it could be too much for the processor, and you could fry the processor. So here's one of the most common places you'll use a resistor. Always a LED has a current limiting resistor. So the idea now is the current, remember, current is voltage over resistance. We have the voltage here from the pin of the processor. You subtract the diode drop of the LED that might, again, 0.6 is a typical number. And then you pick the value of this resistor so that the current matches what you want to do with how bright you want the LED to be. So LEDs always get a current limiting resistor. And if we go back to DigiKey, they list 26,000, not LEDs, 26,000 types of LEDs. And so if you scroll through the selection, brightness in millicandas from 0.01 to 6,000. If we go to wavelength from 390 to 10,000, from IR to UV, huge range is available for LEDs. And we'll talk more about them in output devices. Now we get to transistors, which are the real workhorse of the class. So there are two main kinds, bipolar and MOSFETs. We're going to largely just be using MOSFETs. So a bipolar transistor is drawn like that. And the current in this loop is proportional to the current in that loop with gain. The reason we don't use them standard is because they're always drawing current to work. Instead, we're using what's called a MOSFET, metal oxide semiconductor field effect transistor. So there's two kinds of MOSFETs. This is a P MOSFET. This is an, sorry, I said that backwards. This is an N MOSFET. This is a P MOSFET with this little circle here to show the difference. They have a gate. Then there's two connections called a source and a drain. The gate sets a resistance between the source and the drain. So let's go to the data sheet. So this is one of my favorite parts. This one is 20 cents in quantity. It goes up to 30 volts and 1.7 amps, which is enough for a large motor. And then let's look in more detail at the data sheet. So it tells you which pin is gate, source, and drain. And then this is the key plot. So this axis is the voltage between the drain and the source. This is the current. And then each of these curves is the voltage on the gate. So a perfect insulator would be a horizontal line. A perfect conductor would be a vertical line. And so as you start increasing the voltage on the gate, you'll see initially it's not, and a resistor is a straight line. Initially, it's not really a resistor because it's curving, but as the gate voltage goes up, what you're actually doing in the physics is there's an insulator, then there's a conductor, and then this is a semiconductor that has the gate and the drain. And when you put a voltage on the gate, it's putting charge in what's called the channel. And so it acts like a variable resistor. You're varying the resistance with the voltage. And then the slope of this is a key parameter called RDS. RDS is the resistance between the drain and the source. That may sound abstract, but this is going to become a hugely important parameter for you because power in a circuit is I times V, and then that equals I squared R. Power is how long your battery lasts. It's how hot it gets. And so when we drive loudspeakers and we want the music louder, or when we drive motors and we want a bigger motor that can handle a bigger lift, you need more current. We're controlling the current through a MOSFET, and the resistance of the MOSFET sets the power, and it'll get hot if that's large. And in fact, very easily it'll overheat. And if you have too much dissipation in your transistor, the circuit will shut down, or you can fry the transistor. So we want RDS to be as small as possible so that the transistor doesn't get hot and the power gets to our motor. So that's a key parameter for the power transistors we're using. And then the reason why we have two kinds is a N MOSFET the source goes to ground, and then your load is up here, and then you connect this to your power supply. So an N MOSFET is a sink of current. A P MOSFET is the opposite. This is the power supply. This is ground down here. And the P MOSFET is a source of current. Current goes into an N MOSFET. It comes out of a P MOSFET. And again, that goes back to the physics that I'm not explaining today. But it means if you have a load and you want to be able to have current go both up and down, so for example, a motor that can go in both directions, it means you need both P MOSFETs above it and N MOSFETs below it. If the current only goes in one direction, you can just use an N MOSFET. So that's why there's two types of transistors. Regulators we'll make a lot of use of. What these do is, if you have a battery here, this might be, say, 9 volts. And over here, many of the processors we use want to run at 3.3 volts. So let's see. What we do with the regulator is the regulator goes in between. This goes to ground, this is ground, this is ground. And then crucially, there's a capacitor here. So the regulator takes an input voltage. And so this regulator will go up to 30 volts. And whatever voltage you put in that range, it always puts out 5 volts. And crucially, there's always an output capacitor because it's running a control loop, and it needs this capacitor to store, for inertia in the circuit, to store the charge. You can also put in an input capacitor if you need it for the inductance of the connection. So we use regulators to take a varying voltage in and put a constant voltage out. If you need a lot of power from it, then there's a broader subject of DC-DC converters to do that efficiently. So let's see, questions. I'm not sure what, Charles, your question is. So yeah, there's what are called boost and buck converters that can do voltage conversion. They're active circuits rather than simple analog circuits that can do that much more efficiently. So Charles, a MOSFET, just think of it as a variable resistor. It can do whatever a resistor can do, but it lets you adjust the resistance. Op amps, it makes me sad that you'll probably never see one of these for a reason I'll explain. These are amplifiers. What they do is they take a difference between a negative and a plus input, multiply it by a huge number, like 1,000,000, and then you make a feedback circuit between the output and input. And with the feedback circuit, you can make it amplify, filter, do all sorts of convert voltage to current or current to voltage. The reason you won't, the amazing performance, the reason you won't see them is the microprocessors we use, most of them have amplifiers built into them. So for most purposes, you can just use the onboard amplifier. It's only when you're dealing with very sensitive signals, very low-level signals, or you need to do something very specialized, you go to op amps. Then the microcontrollers, you already met them 2 weeks ago in embedded programming class. Then we're going to have a whole class on sensors and then a whole class on actuators. So I won't cover those today. Kieran, MOSFETs are you can consider them electrically controlled potentiometers almost. Again, the reason why is if you take the IV curve for the MOSFET, an ideal insulator looks like that, an ideal current looks like that, An ideal resistor looks like that, where the slope is the resistance. Um, uh, Remember, for the MOSFET, this curve looks like that, where this is the voltage on the gate. So when the MOSFET is fully on, it's acting like a resistor. But as the gate voltage comes down, it's not a normal resistor, it's a nonlinear resistor that saturates. So sort of in this range, it's acting like a resistor that's voltage controlled. But as you go further down in voltage, it's a very different, it sort of starts like a resistor, but it's a saturating resistor and the current stops going up. So in the limits, you can view it sort of like a switch. Also, an ordinary switch like that doesn't care which direction current flows, but for the MOSFETs, it does care the distinction between N and PMOS. So there are special components that are voltage-controlled resistors. The MOSFET is only sort of like it in the limit that it's mostly on and current's going in one direction. Okay, so think of that as an overture. These are the parts we're going to be using, and you're going to spend many weeks learning how to use them. Now we're going to start designing circuits. So I introduced current and voltage. Ground is the lowest level in the circuit, and everything needs to connect. A beginner mistake that experts sometimes make is you have a bunch of components. They're all connected to the power supply. They go to ground, but you forget to connect one to ground. And so there's nowhere for the current to go and it doesn't work. Every instructor on this call at some point has made that mistake. The voltage, sometimes you'll see it called VCC or VDD. Those are terms that come from semiconductors. It all just means voltage. I mentioned you can think about it as how much water is flowing and how high it is. I mentioned I squared R and IV is power, which you're going to care about for heat and for battery. There was a mention in the chat about Kirchhoff's laws. All the currents around, all the voltages around a loop have to add to zero. All the currents at a node have to add up to zero. Those are just some general circuit principles. And so now we get to EDA. So here is a circuit I made. Let's see. I have to remind myself. This one is 4 vector magnetometers. This is related to a few projects today. Each of these devices measures the direction of a magnetic field. And with 4 of them, you can track the position and orientation of a magnet. This is a processor connected to a network. Here's a voltage regulator that takes the network power and brings it down for the processor. So here's a schematic. That's the design of the circuit. Here's the PCB. That's the thing you fabricate. And then here's a rendering of the circuit. So the job of EDA is to do those steps. So generally, the first step is this. Before I start at a computer, typically I start with a piece of paper or a tablet, and I start sketching to just sketch the circuit. Once I have a sense of what I want to do, I enter the schematic. That's conceptual. Then I have to place where the components go. Then I have to route. Route is where do the wires go to connect the components. Then I have to export and fabricate. There are a number of design rules. One is how many layers you make. So when we get to PCB fab, I'll be covering how to make from 1 to multi-layer circuit boards. A detail is angles. When you etch a circuit board, sharp corners etched differently. So generally, you avoid sharp corners. Vias are connections between the top and bottom or internal traces. When you want to distribute power, often you'll have a whole layer of the circuit that's just power. What are called ground pores are here in the PCB, you'll see other than the wires, all of this is one big conductor. Sometimes you do that to reduce resistance, sometimes to reduce noise. So these are all some of the things you'll have to do. You don't need to worry about those today, but you'll have to do. What you do need to worry about are design rules. So this is a board house, and here's a table of its design rules. And so the design rules include what's the skinniest trace, how close can two traces be together, similar to what we did with 3D printing. Each PCB process has design rules. So for example, when you use the milling machine with the rotating tool, the typical size we use is 1/64th. And so that's the smallest gap you can make. When we use the laser cutter to engrave the PCB, it can easily do, this is in inches, 10 mils, and you can actually get a bit below that. So how you lay out your PCB, how skinny the traces are, how close they can be, depends on which fabrication process you're going to use. When you send them to board houses, it gets very expensive very quickly if you go beyond the simple design rules. Then there's a DRC, a design rule check, which is to check, does your board satisfy the design rules? It's very easy, and again, every instructor on this call has done it, to, for example, have one trace going here, another trace going here, and these are so close together that the fabrication process shorts them. So the DRC is to make sure you've respected the design rules. The ERC is, if we go back to the schematic, I've got all these connections to make, and it's easy to forget one. So the ERC is to make sure you actually did all the connections and none of them are connected wrong. And again, every instructor on this call has made ERC mistakes where you forget to make a connection or you have a wrong connection. So how do we do that? So that's what you need to do to design this. The simplest of all things is this was a student who was an artist, and he looked at the parts and he drew it by hand. He was a good artist and scanned it in and fabricated it. No design tools, no undo, no editing, but just for completeness, you could do that. In the early days, we actually did this with drafting tape. We would lay out tape, take a picture, and then etch that. That's not done anymore. These next three, Tinkercad, Virtual Breadboard, Fritzing, all of these are friendly design environments that look like what you're doing, that you place components, many of them use a breadboard metaphor graphically, and then it lets you simulate the circuit. Those are fun to play with, but very quickly you'll outgrow them for anything serious. I'll link these, but skip them. I'm going to focus in now on KiCad. KiCad is wonderful. KiCad is loosely affiliated with CERN. It started as about 6 different programs that all came together into a complete suite. Its legacy is still there. It's still a series of separate but linked programs. And so some of the other tools are somewhat better integrated. But KiCad has matured, so they are much better integrated than they used to be. It's very powerful, extremely powerful, very extensible, and it's an open source project that's freely available. cross-platform, extensible, and very well supported. So here's a KiCad example. So I'm going to start up KiCad. A big subject is the symbol libraries. I'm going to talk more about this in a little bit. You have to get the symbols for the parts. You have to get the footprints that you place on the board. And the part library depends on what parts are in your lab to use. So I have to tell it what libraries I'm using, and I'll tell you more about that. Then I'm going to come back to this part of this video. This is about the librarians. And so the librarians let me get the symbol, the footprint, the 3D package. And Chris, who you'll hear more of, has been managing a library for Fab Labs. Kieran, I'll talk about Fusion in a minute.
Yeah, you need to go to the add-on manager. So now it's an official KiCad add-on.
Oh, in fact, I have to add that, Chris. Yeah. So I'm not. Let me hold off on libraries for a moment. But yeah, I have to add that crucial thing Chris has done to this page. In a little bit, we'll come back to libraries, but I first just want to do the workflow. So after getting set up, here I am in KiCad. So I'm going to start placing parts that are available in my libraries. Now that's the symbol. Then I'm going to, let's see, in this, I'm going to put a resistor. Oh, sorry, let me mention something. If you're European, I said something not quite accurate. If you're European, this is a resistor. If you're American, that's a resistor. Same part, just different convention. So here's a resistor. I'm going to do something useless, which is I'm going to connect it between two pins, but just to illustrate. So now I'm drawing wires and connecting them. Okay, the next thing I need to do is the symbols can come in multiple packages. A resistor can be many different sizes. So I have to tell it what package I'm using for each symbol. Then I'm going to go to the PCB tool, and I'm going to bring in what's called a rat's nest. The rat's nest is all of my footprints, and then I've got these wires between them that just says I need to connect that. So now I'm going to start placing parts. And for example, there you see those wires crossed. So it really wants to be flipped. So I place the parts where they're happy. Now I'm going to route. And there's multiple kinds of routers. So routing is where I draw the trace. There are, and then it can auto-complete. So here I just auto-completed it and it figured out where to go. There's push routers that move traces around the way. There's routers that wrap around traces. Then on the left, you'll see all of those different colors are different layers. So there can be, right now, red is the top copper layer. Now I'm going to make a mechanical layer that's the board outline. At this point, I can already go to the 3D viewer and I can see my board because when I brought in the packages, it brought in the 3D. And now I have to export. So when you go to a board house, almost universally you send out Gerber. In-house, you can do Gerber, but for mods, you can export an SVG. And bring that in, and then you can produce that. So that's KiCad. This is a nice toolkit that generates all the files to go to a board house. This is a nice tool that connects KiCad and FreeCAD. So KiCad can produce a model, This connects it to FreeCAD, so you can take the KiCad model and go back and forth with your FreeCAD design. This is another tool for linking between them. And we'll come to Chris's library in just a few minutes. So all of that was in KiCad. Strong recommendation for KiCad. Then Eagle has a complex history. Eagle was a German startup. KiCad does everything I said. KiCad can do simulation, DRC, ERC is very well supported. Eagle was a German startup. It at some point was open sourced. It was acquired by Newark, an electronics vendor. It ended up becoming part of Fusion. So when you're in Fusion, you have Eagle built right in. The strength is it's completely integrated. You don't need to change environments. The weakness is some of the optimization for electronics design were lost in the migration to Fusion. So it's maybe not quite as convenient for advanced electronics design, but of these options, it's the most integrated because it's a full-fledged part of the environment. These are some other PCB tools. These are tools for chip design. And if you're interested in futures, see, I'll add a link to this class page and put this in the chat. If you're having trouble with Autodesk, reach out to Luciana. We're working closely with Autodesk on it. Fab Futures is where we do 1 month immersions at a much higher level than we're doing here. And we're doing a 1 month immersion to introduce integrated circuit design. Very ambitious. And so videos are getting posted on introducing the tools to do IC design. So link for that. So now we're up to, see, Gerber to PNG, all of that we'll get to in board fab. Now we're finally up to libraries. So in Fab Cloud, we have a few of these projects, but by far the most active one is KiCad. And I'll link directly to that from the class page. Chris, can you briefly just introduce yourself in this? See, Chris was here a minute ago. So Chris has been doing a huge job to take on managing this. This is a KiCad library of all the parts in the Fab Lab inventory. Oh, Chris, are you muted? I'll go on.
No. I'm here. Microphone problem.
Okay.
Yeah, I've been managing this for a few years, like not full time, but trying to have all the parts that are mentioned in the inventory, in the Fab Academy inventory. And the idea is to just make it easier for you to design boards at Fab Lab specifically. So when you use the components from the library, then what you should expect is that the parts that you choose are actually available at the Fab Lab.
Chris, explain the plugin.
Excuse me?
Explain the plugin.
The plugin, yeah. So with a plugin, so it makes it easier to install it. So all you have to do now is to, when you open the KiCad Project Manager, go to Add-ons Manager, click on Libraries, and look for KiCad Fab Lab. And all you have to do is click install and then apply pending changes, and it's there. So, and it automatically installs the symbols, the footprints, and also the 3D models.
It's a huge saving. The library installation is tedious. There's a bunch of setup for libraries, so it's great. Chris took that on. Thank you, Chris. The other very handy thing is these are all component search engines. So if we take our favorite little processor, Tiny 412, what this has for this one, here's schematic symbol. Footprint is what you fabricate. 3D model is what goes into the CAD export. These are free to use because the component vendors want you finding their parts. There's a Venn diagram. All of them don't cover all parts. So when I'm doing something non-trivial, often I might have all three of these windows open because I'm going back and forth among them to find the parts I want. If it's not there, you have to design it from scratch. But anymore, pretty much all the parts you want are in these librarians. And so you'll find when you need newer parts that aren't in the standard libraries, you'll use these component search engines and you'll start managing your own library. Okay, next step is Verilog and VHDL. When you design a billion transistor processor, you don't click your mouse a billion times. You write programs in hardware description languages. So the examples I give you are a mix. Some are in KiCad, and some of them use something that I used long before KiCad was common, which is a hardware description language. So on the left is the hardware description language. On the bottom is an interpreter. Up here is the render. And then I'm describing, so first, all the different outputs are just different definitions in the hardware description language. It's not clicking and dragging. And then I'm describing the circuit board not by physically drawing, but by writing relationships. So I describe how a part is related to other parts and where I want it to place. And so this lets me make hierarchical parametric PCBs, where there's whole groups that move relative to other parts. There's modules you can reuse. It's PC design as a programming task. And so for many purposes, it's much quicker for me to describe something this way than by clicking and dragging. I don't recommend this as beginners, and this is what you do for very advanced circuit design, but some of my examples will be done with that. And then, let's see, Quentin, are you on the call?
Yeah, I'm here.
Yeah, can you explain SVG PCB?
Yeah, so I was interested in Ian's way of making boards, but it wasn't super easy to share with other people. So I worked with my good friend Leo McElroy, that some of you might know, and we made this JavaScript version. So it's
So,
the code is on the left and the board is on the right. And actually, you could drag one of those red dots.
yeah, so I'll show it. So now
Yeah,
this does something the advanced EDA tools don't do, which is I can click and drag here, and you see parts are moving with it. But at the same time I'm dragging it, you see the program is updating over here.
and
Then I
vice
can go to the
versa. Yeah,
program and I can edit the program. So I can edit the program and update the GUI, or I can edit the GUI and update the program. And that cross coupling, even the most advanced tools don't do. So this is a paper they wrote on this tool. This is not standard, but it's really interesting. All runs in a browser. You could do all of the class using SVG PCB. Quentin, do you know this? This is a newer one Leo's working on. I don't even know the status of this one.
it should be usable, but it's graphical only. I don't think there's code for that one.
Okay. So these are fun options to play with. Thanks, Quentin. And then finally, these are sites that you can use to share your boards. Both share them openly and buy and sell them. Okay, two more topics. Simulation is increasingly important. So WOKWI is almost wonderful. Wokwi lets you pick a processor. Then you can take, it has an emulator of the processor. So you can pick code. I'm doing it from one of my class assignments. You can load the code. And then now I'm going to build the circuit. So here I have to find the pin out is which pin goes where. Now I'm going to start adding components. So I've got a button. Connecting the button to ground. Now I'll add an LED and a resistor. I will connect that to ground. Then I need to know the pins, so I'm going to wire it up. And now the exciting thing is I can run my program. And so when I push the button, the LED lights up and I get a message over USB. So Wokwi is a nice interface. It has pretty much all the parts we use, and it lets you run the code on all the processors we use. That's the good side. The reason I say almost is if you did all of this without the current limiting resistor, it would still work. Wokwi is doing digital simulation, but not real analog simulation. But it's very powerful for the digital. Falstad is wonderful. This is an analog simulator that has all sorts of circuits built into it. And then this AVR8GS is a link between a software emulator for the AVR family processors and Falstad for simulation. And so this is what's called true mixed signal simulation. It's both digital and analog. So what I'm going to do here is, I had mentioned before capacitance, step response. Here I'm going to simulate charging and discharging a capacitor. And this is what we're going to use for proximity sensing, interface sensing, where the resistor is in your circuit and that capacitor there is you. That's your body. So we're going to sense charging and discharging you. And I'm going to add a probe. And so I've made my analog circuit. And then what I'm going to do is I'm going to write AVR code to talk to the pin to do the charging and discharging. And then I'm going to run my digital code, but looks at what it does for the analog circuit. Okay. So now when I run it, it's the scope here is showing charging and discharging. And then if I change values, it changes. So Sahin is asking, it's Arduino code for AVRs. So it understands Arduino code structure, but in particular, it's for AVR family. So what just happened in this last bit is the digital simulator is running. And if you look down here, I'm going to vary the amount of capacitance, and that varies how quickly it charges and discharges. And that's what we're going to be using as a sensor. That the charging discharging rate lets us sense the capacitance, which is going to turn into who's in the electric field. Okay. Then SPICE is what you use to simulate integrated circuits. That's industrial strength simulation. LT-Spice and ng-spice are freely available versions of it. And then KiCad can export SPICE. So you can export from your KiCad model into a SPICE simulation, similarly a fusion. Okay, so that's simulation. Here's the last item. You're going to design circuits, you're going to make circuits, and then the circuits won't work. So test equipment is one of the key things for debugging. So this is a power supply. It lets you control voltage, and it picks current, or you pick current, it picks voltage. It's handy because you can dial it up slowly to see what happens as you power, and then it can tell you how much power is being used. So handy bench tool. This is a multimeter. We use those all over the place. We use those to probe voltages in the circuit. You can measure currents through it. You can measure resistance or capacitance. The only note with it is when you probe a circuit with it, once you have components soldered, the readings can be misleading because there can be shorts through your components. So before you solder, it's good to see if there's shorts. After you've made your board, one of the most common uses is to probe voltages. So for example, if you have a component misbehaving, you think you're putting out 3 volts, but the meter will say it's only 1.5 volts. And that's because there's a misbehaving component putting too much load on it. So measuring voltages in the circuit is a standard debugging. Oscilloscopes like this are a standard bench tool. They let you see the signals. You can pick when it triggers to show you the signal. And then one like this, increasingly, these all know how to do logical decoding. So along with analog signals, you can give them digital signals like USB, and it can decode the digital signal to tell you the USB message, while at the same time you look at the analog signal to see what the circuit is doing. And then there are these little cheap and cheerful logic analyzers. When you're debugging a complex circuit, you may need to watch multiple leads. So these let you connect to multiple leads. It stores the data and then lets you study what's happening to the digital signals. And then a more expensive one is these devices. What these let you do is full mix signal, where simultaneously they're measuring analog signals and digital signals. Let's see, Adrian is putting in the chat a link to, okay, nice. Adrian, you should have noticed by now, documents well. So this is, the logic analyzer gives you this sort of data coming from it, and then you can decode the signals. So these more advanced mixed signal, these more advanced mixed signal debuggers, these might be $500 instead of $50, but are really powerful and really useful. And so the group assignment is take, we're starting an Adrian channel. Take a microcontroller board in your lab that's running. Take the one the QPad, if you use that from 2 weeks ago, and use the test equipment to watch it running. So for the QPad, you could watch the I2C signals and decode the I2C message. Something that's eye-opening is take the power supply and the ground and just look at the power supply and ground. And if you look at the power supply, it should look like that. But often when you look at it, it sort of looks like that. It's really messy just because of the inductance and capacitance and the loads. And so the group assignment is take the test equipment in your lab and analyze the signals. Look at a circuit board, and that's to get ready for debugging your own. Individually, I want you to simulate a circuit. Let's see. Dylan is asking for the logic analyzers. The cheap $10 ones tend to work surprisingly great. Less good for mixed signal analog. Simulate a circuit. The circuit could be any circuit, or it could be one leading to your final project. If you browse Wokwi, it's fun to browse it. You pick your processor. They have featured ones. You can pick your language, but then they have all of these parts that you may end up wanting to use in your projects. So you can start by playing with simulating those. Then use an EDA tool. If you're already happy in Fusion, that's a fine choice. If in doubt, I recommend KiCad as powerful, freely available cross-platform. I want you to design with parts from the inventory so that they should be in your lab. And then crucially, I want you to design it with a microcontroller. You could start from the bare part, like a ATtiny 412. You could start from a module like a Xiao or a Pi Pico, but design a microcontroller into your board. And then I want you to run a design rule check to make sure you can fabricate it. One extra credit is try another design workflow. And then the second one, and I'll add a word to this, is when I say design a case, these tools, the EDA tools interface to the CAD tools. So you can export your board into a CAD tool and then design a case around it as a design exercise. And then to look ahead, in 2 weeks, you're going to be producing the board that you designed this week. So to look ahead to that. So the goal this week is to get you designing with the EDA tools. And my advice is, especially if you're happy with Illustrator and Rhino, you're going to find the EDA tools annoying to start. They don't accommodate you. They force you to work in their workflow. But then I also predict you'll find as you get used to them, you'll find they're right, you're wrong, which is their workflow is constrained for good reasons. It's a structured way to do this, and you'll benefit from learning how to work within its workflow. Work through the learning curve. The goal this week is to get you designing. At the end of this week, it's not frozen. You'll keep working. At the end of this week, you should have schematic PCB layout renders and simulation results. And then you can keep updating, and in 2 weeks, you'll start making the boards. As usual, any questions, global open time, and no recitation this week. And we have sustainability coming up after that. Final questions, comments? If not, welcome to the wide world of electronics design. And also, yeah, you don't have to be boring. You don't have to just make rectangles and straight lines. You can make interesting expressive designs as part of what you're doing. Okay, happy PCB designing. See you in a week.
Adiós.
Görüşürüz. Bye.